Okay, so let's look at a problem like I sort of set up yesterday, where you've got your little tank of sharks or whatever down here, and here you are standing at the top of this ledge with your kitty cat. Remember, I don't actually endorse hurting animals. I know that the cat will be fine. They're just fun to pick on. So there's our cat. It's enormous, apparently. What we're going to do is we're going to give the cat a little toss upward, and then what we want to do is track its path as it goes up and then eventually lands below here. So a couple things to sort of identify on my drawing, and then we're going to get into the graph. Really quickly, we have an initial position, um, which technically, actually, I'm going to use Y because we're looking at vertical. So there's our initial position Y, or X. We've been using X, but let's go with Y. And then we have an initial velocity in the upward direction, velocity initial in the Y direction. And then we have a final vertical position, Y final. Now, how does this look on our graphs? So let's look at position versus time. So here's my position versus time graph. Actually, I know, let me back up here. Let's assume that I've decided to call my origin here. So y equals 0 in terms of position there. So we know that's where the final position is going to be. I can identify y. Oops. Trying to do this quickly. Here's my initial position, y, and then we know that we're throwing it upward, so the cat's going to do some thing like that. So then quickly, let's look. What does our velocity graph look like? Okay, so we have time, seconds, we have velocity in the y direction. We have an initial. If I go over here and overwrite this in a different color, should overwrite this in a different color. This is our initial velocity, and it is positive. So that would correspond to something here. So here's my velocity initial in the y direction. And even though, so this is probably one of the most confusing things. The position continues to track upward here. That does not mean that the velocity continues to go up. As soon as that cat is thrown upward, its velocity begins to decrease. In fact, we know that at this position right here, at that position right there, velocity equals 0. So that means at that same time, whatever that time is here, if I say there's that same time, now I can draw my line to say this is what my velocity graph looks like. Or again, the velocity is 0 at the same time here as it is here. Lastly, what will my acceleration graph look like? Time, acceleration. So a real quick reminder that this is the last piece in terms of looking at these different graphs. When moving from a position time graph to a velocity time graph, and then from a velocity time graph to an acceleration time graph, the way that they are related is that a velocity time graph, the value at any given point in time is equal to the slope of the position time graph at that same point in time. Calculus friends, that is referred to as the derivative. It is the derivative at any given time. Non-calculus friends, guess what? You're doing calculus, and it's really not that hard, so don't be intimidated. So here we go. Let's start with the one that we were already identified. At this point up here, if I zoom way in and keep zooming way in, the slope of that line at that point in time is 0. It's a horizontal line. So if the slope here equals 0, then I can zoom out and go, okay, well, at that point in time over here, since this graph corresponds to the slope at any given time, the slope there is 0. Now let's go back and do another one. Let's look initially. We had a pretty steep positive slope. So over here, we have our largest positive velocity. Partway through the motion, we had a less steep positive slope. So a lower positive velocity. And you can just see how this keeps going. Now over here we have a less steep negative slope, which corresponds to a negative velocity. And notice that the steepness of the slope increases until we have a pretty steep negative slope corresponding to a larger negative velocity. Now, if we think of that same pattern as we go from the velocity graph to the acceleration graph, this is a simpler situation. Since the velocity graph is a straight line, it has a constant negative slope all the way down. With that constant negative slope tells me that I have a constant negative acceleration, which would look something like this. And yesterday, our little exercise in the lab, we even know that this value, if this is truly free fall, there's no air resistance, that value is equal to negative 9.8 meters per second squared.